Hi everybody, in today's video we are going to have a look at the 2022 higher level paper question 1. So this is an experiment question. Traditionally there would be 4 experiment questions, do 3. In 2022, because it was a year that was affected by COVID, there were 5 questions and you had to do 2. So you had just had a few more choices, but for the purpose of going through this question, it doesn't really matter. We'll answer it the same way, no matter how many choices we had. This one looks quite long, but I think that's mostly because there's just lots of little parts in it, and a lot of these parts can be answered fairly short answers, a sentence or two or a small diagram, but we'll break it down and we'll go through it. So how we're going to tackle this today is I'll have a read through the question. We'll just get a feel for what's involved as if you were in your exam yourself. And then I'll break down each piece and give a sample answer for it, give you an idea what would be a good answer for these kind of questions. Okay. Before I do get into it, and I'll be pointing to this in a minute, but I also have a sample answer available. So if you've the best thing anyone can be doing if you're preparing for your exams and you're studying and you're revising is to be trying out questions as if you're in an exam. So have your book closed, put away the computer, pull out a blank sheet of paper, and just have only the question in front of you and see how much of it you can do without getting stuck, testing yourself basically. Okay, that's my main thing here, test yourself. So if you're feeling confident, if you've done that and you're looking only to see would your answer kind of match up well, I have sample answers that you can have a look at and compare and see, are you kind of in the right area? If when you do that, you have questions, you can always contact me and I can help you out. If there's something you said, well, look, I said it this way, would that be acceptable as well? Yeah, no problem. I can have a chat to you about that. But also, this is what the video is handy for. So I don't believe that you need to sit through the whole video. If you're feeling, medium level to high level confidence and you have already an answer, your attempt made, and you just want to check your answers, just pause now and go straight off to the sample answer. If on the other side of things, you're really not sure how you're doing with this and you kind of tuned in because you wanted to see an answer, I would advise pausing also, because if you watch me doing this and you think this sounds grand, yeah, that all makes sense. It always makes sense when someone else is telling you the answer. Of course it does. That's not really preparing you. You need to pause and go off and do like I just described and test yourself. Okay. There's my warning. If you have questions on the marking scheme as well, I can go through that with you. I tend to take a bit of caution around the marking schemes because they change a little bit from year to year. And if I tell somebody that their definition got them 3 marks this year, it may not get them 3 marks next year, and so on. That's kind of a bit of caution around the marking schemes. But if you are trying to really push for those full marks and you're trying to see what do you need to do to get every mark you can, they are a handy resource as well. So if you have questions on them, let me know too. There's no question too big or small, really. I'm really hoping to make sure everyone is getting use and getting a lot of help out of these videos and sample answers. All right, there's my warning. So let's have a look at the question. And on the 2022 paper, this would have been the first thing in front of you. So just imagine yourself inside in your exam hall and you open it up and you're having a read off this, okay? So a student used a meter stick to investigate the laws of equilibrium for a set of coplanar forces. He found that the weight of the meter stick was 1.2 newtons and that its center of gravity was at the 50.6 centimeter position. Okay. Hopefully you might be thinking, okay, it's my equilibrium experiment. It's written here in the question anyway, and you're kind of bringing that experiment to mind and you're starting to think about the diagram and your steps and how you did any of the calculations, okay? I'm going to have a little look through this. And again, with these videos, I'm trying my best so that no matter where you are on your kind of learning or confidence, you can kind of get what I'm talking about. But if you're finding that it's going a bit slow for you, well, you can let me know, but also you can skim on a little bit, okay? So I want to have a look at some of the phrases in the sentence so that we understand what we're talking about. So a student used a meter stick to investigate the laws of equilibrium. They're going to come up in the one of the questions. So I'll explain them when I get to them, but this is telling you anyway, this is the experiment that they're hoping that you're thinking of. This is the experiment they're trying to test you on in this question. Coplanar forces mean forces that are on the same plane. They're on the same level. In this case, we're kind of using a meter stick like a plane, and they are along that same meter stick. That's all it means, same. The weight will come up again. I'm going to give you a word of caution about being careful to make sure you know the difference between mass and weight, but that's going to come up in this question. And anyway, weight is in newtons, so that could be a hint for you as well, that you're looking at newtons and not kg. Okay. And then its center of gravity. We need to know its center of gravity in probably straight away before we even start the experiment. And it's kind of like the point at which everything moves around, okay? So just trying to highlight some of the bits in the question, okay? So they've described an experiment that a student is doing, and they've given us a few bits of information to get us started. Okay, now we're into what is your examiner hoping for you to do? Part one here. So here we are. Describe how the student determined A, the center of gravity, and B, the weight of the meter stick. So what I'm going to do, I'm going to give myself a bit of space. Don't worry, I'm not going to remove all these questions. I'm just moving them down out of my way so that I have some space to write in a sample answer for you. And we are going to start answering the questions. Oh, sorry. No, we're not. I'm going to have a read through the other parts first, okay? Because I'm always guilty of this, of going straight into answering it, but you need to read through just to get a feel for what else they're looking for. As I said, there's always choice in that part of the section A is the experiment section. There's always choice. So make sure you have a look through it and see that you feel that there's nothing too weird that's going to catch you out. What you don't want is to, be plowing away through your question and find yourself, down here somewhere and you're stuck on something, and that's something like an 18-mark question. It's half the question, okay? So a lesson learned for myself there. I need to have a look through these. So on part two, so you're wanting to know, how do you find the center of gravity and how do you find the meter stick? And in a way, they're kind of stepping you through the procedure, because those are one of the first steps you take in the experiment. And here's they always like to put the harder questions are the why, okay? Because we would expect, especially 6th years, you'd have your kind of diagram and you'd have your steps, but when they come in with the why questions, that's where they're trying to find who really knows what's going on, okay? So why was it necessary to determine the center of gravity of the meter stick? Why do we care? Why are we doing that? It's easy enough. Well, for most of us, find it not too hard to rattle off a procedure, but why are we doing these steps? Okay, so we'll answer that too. And then the student, he then applied vertical forces to the meter stick. So think up and down to the meter stick and adjusted them until the meter stick was horizontal and in equilibrium. So that was completely flat, parallel with the horizon, and in equilibrium. And equilibrium just means it was stable. It was, and there's a question on that as well. So it just means that it wasn't out of balance, basically. Okay, so he did these extra steps, and we're going to have some more questions on that. So show on a label, indicate, excuse me, I converted that to show, indicate on a label diagram how these vertical forces were applied to the meter stick. This is your diagram from your experiment that you might have maybe learned off or practiced coming up to the exam. So this is just your diagram for your experiment. How was it ensured that the meter stick was in equilibrium? So they're checking partly that you know what that means. What is equilibrium? And how do you know that it's in equilibrium? And we're going to get to that too. And what was the principal advantage of ensuring that the meter stick was horizontal? So this is a bit of a one for the thinkers as well, okay? And we're going to deal with that too. Okay, so your student is after setting up his experiment, and then he's going through it and he's after recording some data, and they're giving you that, okay? So these are the following data. We have a table, the position on the meter stick. So this is just literally the centimeter marks on the meter stick. Kind of a spoiler, but you're going for the label diagram, but you're going to be hanging weights at different parts and putting Newton balances on different parts of the meter stick. And this is the place where they were. So they're trying not to give that away in the table, but that's what's happening. So you had something maybe hanging or something suspended at 22.5 centimeters and so on. And that weight hanging might have been, oh, sorry, I'm looking at it downwards, might have been 2 newtons, or you might have been pulling a Newton balance up at 2.85 newtons. If you're getting a bit confused what I'm saying here, it will make more sense when we have the diagram in front of us, okay? So don't be too worried just yet. I'm just trying to describe what's going on the table. And you've got upwards and downwards directions. So these are all our vertical forces that the student added. So he applied vertical forces to the meter stick. That's these, okay? That's what's in the table. And what they don't ever give you a data table and not ask you to do anything with it. The first thing is calculate the net moment about the 0 centimeter position. And maybe it's coming back up in your head. You might be thinking of like clockwise, anti-clockwise moments, things like that. That's where we're going with this. So if that's kind of ringing a bell, you're on the right track. What are we? Part 7, calculate the net vertical force acting on the meter stick. So you're thinking forces up versus forces down. And lastly, explain how these results verify the laws of equilibrium. And you could probably talk about that for a really long time, but basically what they're looking for is for you to say, these are the laws of equilibrium, and how does my calculation compare to that? So it doesn't need to be massive, okay? All right. Now I can get into my answering the questions. I was a little bit eager there to start with. So if you're watching along and you're saying, look, I got stuck on like part 4 or part 5, you can jump on. Okay, I'm just giving everyone permission. Nobody needs to sit through the whole thing. Jump on to what you need. Okay, make this the most useful for you possibly can. Okay, I'm going to clear off my scratchings that I was using just to follow where I was. You can always do this in an exam, by the way, if anyone's here wondering. You can scribble all over the marking scheme or the exam paper if you want. It's yours to do what you like. And whatever helps you to highlight the important parts of your question, just go for it, I said. Actually, when I am marking papers, I like seeing the students have done that because it means you're reading the question, you're picking out what's important. Okay, gonna go back now and look at part 1 where we describe how the student determined A, the center of gravity, and B, the weight of the meter stick. And I'm going to give myself lots of space just to put in an answer. Okay. Now, I'm going to use my sample answer that's also available to you, but I'll just put it up and then I'll explain what I'm saying, okay, just to make sure it makes sense. Now you might read it and go, well, duh, I got it. So let's see. Here's my sample answer. You should be seeing that on the screen, I hope. And I will just take a piece and bring it over to our whiteboard so we can have a look at it better then, all right? Oh, 2 pieces. I'll start with part 8. Sorry, guys. So this scanned in, like, I can read it, but it could be a bit less faint. So if you're finding you have any trouble reading it, do let me know. Can use a different setter on the scanner or something like that and make sure that we can read them. So this is part A. I'm going to just label that up for myself. So you want to know, how did the student find out the center of gravity? Okay. The center of gravity was found by suspending the meter stick on a piece of thread at approximately the 50 centimeter mark. I'm going to stop there. Likely what you did when you did this experiment, and there are a few ways of doing it. So this is where you might say, oh, well, I did something where we balanced on our finger, or I did something like that. Is that okay? You can let me know. It likely is, okay? Because as long as you're getting it into equilibrium, you're doing it. So as long as you're finding center of gravity, you're doing the job. There's many ways to do it. So in this case that I've picked, what you might have done is had a retort stand and had a piece of string, like a loop of string, hanging on the retort stand, and put your meter stick in there, put it so that the string was at about the 50 centimeter mark, and just let go. So it's suspended, it's just kind of hanging there. And you might have had to adjust, not all meter sticks are exactly at the 50 centimeter mark. If they've got a little bit of meter stick before the 0 or whatever, adjusted it until the meter stick is balanced and exactly horizontal. So it's exactly, parallel with the floor. It's not moving around. It's not tipping over to one side or another. It's staying balanced. It's staying still. It's horizontal. And wherever your string is across your meter stick, that's your center of gravity. I would say that's probably enough for this question, but I have seen answers where a spirit level, like a bubble meter level, was used to verify that the stick was horizontal. So if you don't know what that is, have a Google Images search, or I can put one in here maybe. It's just a level that has a water and a bubble in the water, and as long as the bubble's right in the middle, you know you're horizontal. Okay, so sometimes you could be really sure and put that little spirit level up on top of your meter stick and make sure that it's perfectly level. Okay, that's how you get your center of gravity. The second part of the question is asking you for the weight of the meter stick. So again, I'm going to give myself a bit of space. I've actually quite big writing, and that's partly why I'm not using my drawing pad here, because my writing's very big and it fills up space very fast. So we'll jump. Oh, sugar. I've been talking through it on the sample answer, but that's okay. We can use that. Sorry about that. So I meant to change my screen back, but it actually doesn't matter because I was looking at the same piece of text. Okay, we're going to have a look now at part B. And this time I will try to remember to put myself back to the whiteboard. So in case I forget later on. Here we go. Go back up there. You probably are going, what is she talking about? But we're going to all jump onto the same screen now. Amazing. So there we go. So now what you should be looking at is my whiteboard where I have my question and my answers all up here together. Yeah, that's perfect. Okay, sorry about that, guys. We're technical difficulties a little bit. So this is part B of the question, where we're asked to describe how the student determined A, center of gravity. We just did that. So we're describing how the student did B, the weight of the meter stick. Okay. Now, this catches some people. And I think they are being clever on purpose to see, can you compare the weight compared to the mass, that you're not getting caught up. Okay. So the mass M of the meter stick was measured on an electronic balance. And now we're talking in our house, in our kitchen, our bathroom scales, we kind of call them weighing scales, and it makes us think that we're getting the weight. We're really getting the mass. So we would have, in our lab, we put our meter stick up on the electronic balance. We would have gotten some result in kgs or grams, but that's our mass. That's how much stuff is in our meter stick. It's not actually the weight. It's not taking account of the force of gravity, which is the difference between mass and weight. Mass is just so many kilos, so many grams. It doesn't matter where you are. If you're on the moon, you're going to have the same mass. But if you're on the moon, you're not going to have the same weight because there's a different force of gravity working on that meter stick. So you need to do that extra step, right? So a lot of people will probably get to the electronic balance. And honestly, if you were even stuck in your own electronic balance, you've kind of got step one. But very importantly, you need to be using the weight is equal to mass times gravity. So the weight of the meter stick is then calculated using weight is equal to mass times gravity, where G is acceleration due to gravity. Okay, so I just wanted to say what every letter meant. And just in case you're not that familiar with this equation, I'm going to really write it all out. And again, if you are, great stuff, you're able to move on. But just for anyone who's maybe a bit rusty on this, been a while since you used it, not too sure about it, looks a bit familiar, but what do each of the pieces mean? Okay, so we've got weight, and that's, I'm going to put your units here for anyone who's really getting good at the units. They're a very handy way to figure out what goes where sometimes. Okay, so you've got all your units here. So you've got weight is in newtons, mass is in kg, and gravity is acceleration due to gravity, really. So it's an acceleration, it's mass, ms to the -2. So meters per second. Sorry, I said mass and threw myself off. Meters per second squared. Okay. You don't need to give what I just scribbled there for your answer. I'm just explaining this for you in case you're wondering where that formula came from. Alrighty. We're ready to move on to the next part. So again, you might be finding this kind of slow going, or you might just be checking your answer and be going, yes, I got it. So everyone's a bit different. Why was it necessary to determine the center of gravity of the meter stick? So remember I said that that's the one that might catch people out if you've not been thinking about why are we doing these things. So let's get into it, because we might all remember how we did these things, but why did we bother? So the center of gravity We want it because later on in this question and later on in this experiment, we're going to be doing calculations. And you may remember doing like anti-clockwise and clockwise moments about a point. The center of gravity is our point. It's kind of like fixing the middle of the clock. We need to know what other things are going anti-clockwise compared to that point. It's basically a reference point, okay? So I have a sample answer for that, and I'm going to just stick it in, but I'll just make sure it's clear as well before we move on, okay? It's not the longest answer ever, which is nice. And it's a handy one, okay? So it's something to remember. It's really just a reference point. You could get really tangled in this one, but it's just to give us something to have our calculations all based around, okay? So here we go. This is the sample answer I gave for that one. The center of gravity gives us a reference point around which we can calculate the clockwise and anti-clockwise moments. All right. So you could get really caught by that. But it's actually nice because it gets you a nice few marks as well. So it's a handy one to know. Okay, we're ready now for when our student has moved on and he's applying forces to the meter stick. So we're ready to go on to that part where he is where he's doing that, and we've got a few more questions to go with that one. So I'm going to move them up for you. Hopefully that's coming up clear enough on the screen. I really definitely want to hear if anything looks a bit weird because, sorry, we need to go down a bit. I want to make sure these are useful for you guys as well. And there's not much point me making them if people are finding them helpful. So definitely give me any feedback on what works for you, or if the screen is just moving around too much and things like that, you can work around that too. Okay, so here we go. The student then applied vertical forces to the meter stick and adjusted them until the meter stick was horizontal and in equilibrium. So there's up and down forces being added here. And the very first part, as you'd expect really in an experiment question, is to give a label diagram. Now I have my sample answer label diagram too, but I do find that it can be helpful to actually see how I built up the diagram. So I'm going to give it a go with my pen here, because if I just paste in a diagram, you like same as everything, you go, okay, that looks okay, but would I remember all those parts when I'm doing it myself and what's important and things like that, okay? So I'm going to give myself loads of space and we're going to do a label diagram. Now, if you already have your one, it could be a time to check that you have the bits that I have, and that would be a really good idea just to have yours ready in front of you, okay? Okay, so downward, it's also asking just to be careful here. It's not just saying draw a label diagram, but to indicate on the label diagram how the forces were applied to the meter stick. So I put also a bit of text with mine just to make it really, really clear, but the diagram will probably cover you, okay? So I'll do the diagram first and then I'll explain why I put a sentence in, okay? And this is the standard diagram that comes with this experiment. So as long as you are comfortable with this one, you can probably make a really good effort at any questions that will come up in this experiment, okay? So I am going to start with my meter stick. And because I have the luxury of being on the computer, I can just use squares on my paint, but I'm just doing a square. And up above it, I'm drawing basically like a stick or a pole, but it's just a support, okay? It could just be anything on the retort stand. Most likely it is something like your retort stand. And that's our support. We label everything when we're done, okay? I had a look at the data points that they give you in the table below to kind of roughly get my balances and my weights in the right order, but like it doesn't really matter because if you're going through this question, you haven't seen that part yet and you put weights and balances in the wrong order, you're still answering the question, you're still showing how they applied the vertical forces. So let's break it down. Vertical means up and down. So we're applying some forces up and some forces down, okay? And Newton balance, I've mentioned it a couple of times, and I would hope that you would have seen them in the lab. It's basically like a spring and with a hook at the end of it, and along the edge of the spring there's a measurement. So if you put like your hand or anything on the hook and you pull the hook, so you're pulling out the string, there'll be a little measurement showing how much force you're putting on it, okay? So the more you pull, the higher Newton reading is going to come up on the side of the spring, if that makes sense. So I'll start here and I'll just put one on. I'm just going to freehand them just to give you an idea what you might be doing yourself in your paper. If you're feeling, some people love diagrams, I like them, but I do find I need a bit of practice sometimes to make sure I have all the right details in all the right places, okay? So it comes usually with a hook on the top. We'll tie that to the top. And oftentimes in this experiment, we might use a paper clip or something of like a very small negligible weight, meaning I can ignore it. And the Newton balance is hook in there. And inside this, it's like a plastic, usually it's like a plastic box with a spring inside it. And there's a little marking that shows how much I pulled on it, so how much force I'm putting on it. I'm going to call this NB1, Newton balance 1, because that might be helpful for us later. And there's two of those, and those are my upward forces. They're holding the meter stick up, and I'll just have another down here, similar job. And then we'll start moving on and talking about our downward forces, which are the weights, which I've mentioned as well. And again, I hope that these would be seen. If it's something that you're not too sure of, have a look on an image search, have a look in your textbook. I could bring up pictures of them as well, either if anyone is really stuck. Okay, and I'm just going to put a marker there to show how much. I would read that in person in the lab. I would read that and I would say how many newtons is written on it. Okay, so there's no calculation involved. You just read it off the meter, off the Newton balance. Now those are upwards, so they're just holding the meter stick up, and we want to put some down to see can we balance them out. Okay, so we've got weights in this case. Usually they're kind of like thick coins a bit, and they're very hefty. And they come with a little kind of tray that you can hang them on. So you've got like a flat part like this, and you'll hang a couple of weights on it. It doesn't really matter how many you draw, but they're kind of like metal discs and big chunky ones. They're surprisingly hefty, and you stack them up on here, and you're going to hook it onto the meter stick. I'm going to call that W1 for weight 1. It might be handy later. And if you just wrote weights, that's fine. That's fine. If you're just looking at your diagram now, that's completely grand. I'm just thinking ahead because I've looked on at the rest of the question and it might need it. Okay, so you've got a little circle, not very artistic. And the reason I'm doing my own hand drawn one in front of you is to give an idea of what you need, how much detail. That's something that I would have kind of been questioning, like how detailed does it need to be? It doesn't need to be photorealistic or anything like that. Okay. You might be looking at this going, looks fab, but we are missing our labels. So I'll just call this support, or it could be a retort stand, but it's just a bit complicated to draw two retort stands. And you know, you're in your exam and you have limited time, and the retort stand is not really the important part. It's just that they're on hanging on something fixed. Okay, this is the star of the show, the meter stick. And over here, up here, we've got our Newton balances. And you can see how I was talking about my ratings very large. Newton balances, we've got two of them. I'm okay with labeling just the one because I understand that that's the same thing. Unless your drawing is really, really bad, it should be pretty obvious that you mean that they're both the same. And weights, okay? And these guys. All right. So this is not part of your drawing, but like just to make it really obvious, I'm going to cheat a little and use some triangles or some arrows. I mean, the Newton balances are, nope, not that one. Sorry, they're pulling us up. I'm going to take advantage of the fact that we're on paint. Okay, and the weights are pulling us down. So we've got forces up versus forces down. Okay. In a minute, we're going to also talk about clockwise and anti-clockwise moments. And those ones are going to be in comparison to the center of gravity, which is like here. Now, this wasn't really part of the answer to your question because they were only asking you about the vertical forces. And I'm going to just write COG, center of gravity. I'll come back to that later. This is just me preparing you for the next part that's later on in the question. All right. Okay. Hopefully that looks something similar to what you had yourself. Hopefully it's helping you to remember this experiment that you should have done in person. And I'm going to be that little bit extra because we're really aiming here to just make sure we squeeze every last possible mark out of our examiners and just make it super, super clear what we're talking about. Really make sure you're answering the question. The question was, indicate on a label diagram how the vertical forces were applied to the meter stick. I think you have it done, but if you really want to hammer it home, there's a sentence that I'm going to show you now, or we put it in and see if that just kind of extra clarifies it, okay? So here we go, got some space down here. And downward forces were applied by suspending weights from the meter stick. That's on our diagram. Upward forces were applied using Newton balances as shown in the diagram below. Now we had that above in the other one, so we'll just call that above now. Okay, so if there's questions on it, let me know. I'm going to just be a bit cheeky and write above. That's fine. And we'll keep going to the calculations part next, okay? This is where your student has moved on a bit. He's applying his vertical forces to the meter stick and adjusted them. Oh, sorry, we doubled ourselves up. But he's applied vertical forces to the meter stick and adjusted them. He's done what's shown in your diagram. We've indicated on the label diagram how the forces were applied to the meter stick. And what we want to know next is how was it ensured that the meter stick was in equilibrium? Okay, so we're going to just say goodbye to that. We've that part done. Don't worry, it's up here, I think. Yep. And going to know how did we ensure that the meter stick was in equilibrium? So when they're asking you this question, partly they're checking do you know what that means? What is this equilibrium? So meaning everything is equal, everything is level. So the meter stick, I kind of said it casually earlier, it's in equilibrium when it's not rotating or moving in any direction. It's staying still and it's completely flat. So I'll just I'll put that in from my sample answer because it's a bit quicker than me handwriting it. But it's when the meter stick is not rotating, so it's not kind of going around side to side, one end going up above the other. It's not moving in any direction, just to be really clear about it. It's not bobbing up and down, it's not doing anything else that we might not expect it to do. It's staying still, okay? If it's moving, that means there's a force acting on it, just to get into the more physicsy side, and we don't want any forces acting on it, any net force acting on it. You could have a force up and a force down, but they're balanced each other out. Equilibrium kind of means balanced, all right? And I'm just thinking that just to help if you're not sure. So balanced. How do we know that we're okay? Because if I went up to my diagram, I love a diagram. If I had Newton balance 1 over here, and I had these two sets of weights here, well, it's going to tip because without Newton balance 2, the meter stick's probably just going to fall right down because there's nothing holding it up at this end, okay? And that's quite an obvious example. Like if you were doing that in real life, you'd be like, well, yeah, of course it's going to fall over. I need to hold it up with something. But we're just putting the kind of more scientific physics words on it to explain to somebody, how did I know it was in equilibrium, okay? So that's a nice one. And then another kind of theory kind of one, which is a lot of them actually in this experiment question. What was the principal advantage of ensuring that the meter stick was horizontal? Why do we care? Could we have had it kind of tipped over to one side? And similar to that center of gravity question, the short answer is it makes our calculations easier, okay? I'm going to put a few words about that too, just to make sure that you kind of know what you could say in an exam. But honestly, if you had makes the calculations easier, you really have the gist of it at that stage, okay? So let's see. The principal advantage of assuring that the meter stick was horizontal would be that when it's horizontal, the weights and balances they're applied directly perpendicular, okay? So what do I mean by that? This is getting into like trigonometry, and we don't want to deal with that trigonometry right now. We don't want to do extra maths if we don't have to, basically. No matter how much we like a little bit of maths, if we can do something where everything is nice and perpendicular and it's easier to work it out, there's no angles to think about, that makes our lives much easier, okay? So here is my text to explain that, and let's have a read of it, make sure it makes sense to us. When the meter stick is horizontal, the weights and Newton balances are vertical, i.e. up and down, and they're perpendicular to the meter stick. So they're exactly perpendicular, meaning there's exactly 90 degrees in between them. And in case you are rusty on your parallel and perpendicular, well, I would say you probably shouldn't be at this stage. But we've got our perpendicular. Well, not very perpendicular by me, but like this. Parallel is the one where they're right next door, but perpendicular means your angle is exactly 90. And when we get into it, that makes it easier for calculations, okay? So the weights and balances, the weights and Newton balances are vertical and perpendicular to the meter stick. Momentum, and we're going to get into why are you talking about momentum? But momentum is equal to force by perpendicular distance, because we're going to think about the moments, so the anti-clockwise and clockwise moments, but it's perpendicular distance, okay? It's important that it's just the one working perpendicular to it. If we had used something that wasn't perpendicular, we would need to take account of that angle. And that's where trigonometry starts coming in. So this means that the force measurements can be read from the Newton balances directly, and using your known weights, meaning I picked up in my lab, I put a 2 Newton and a 3 Newton on my little stand, and that's how I know I have 3 Newtons hanging on my meter stick. They're just set weights. Every one of those little metal discs has written on it, I'm 2 Newtons or I'm 3 Newtons, without using any additional trigonometry. Okay, so this is a bit sticky. The short answer is it makes our calculations easier. And then I'm saying, well, why does it make our calculations easier? Okay, because I'm going to be going on looking at clockwise and anti-clockwise moments, and the momentum is totally dependent on you using perpendicular distance. So as long as everything's perpendicular, I'm solid. I can just read my my Newtons off my balances and straight off my meter stick. I'm not doing any extra calculation. But if I was doing this and for some reason I decided to put a 45-degree force one way and a 30-degree another way, I'd be in this kind of d cos theta type stuff, which we can do, but we don't want to have to do that. We don't need to, okay? We can still prove the laws of equilibrium without dealing with any thetas and any angles, okay? That's a bit of probably the stickiest bit in this question. So if you're finding that tough, that would make a lot of sense, and definitely give me a shout if you want me to try and explain it another way or anything like that, all right? Oh, now we're ready to get into the meaty bit that I like, the calculations, okay? And once we get into them, it flies. Once you set it up properly, you should be in pretty good shape. Okay, let's bring them up and have a look what we need to do. Following data were recorded, and we've got a lovely table there. I'm going to have a little scribble on my table. You can do the exact same thing when you're in your exam, no big deal, and it might just help. So everywhere that I see upwards, I'm going to write NB, because I know that was with a Newton balance. Might not even need to, but I'm just trying to make it clear to you what's going on. That's probably NB1, NB2 from my diagram. That's an N. And we've weight 1 and weight 2. And just to make it clear, how did they get these results from our diagram? This is literally where was my paper clip resting on my meter stick, was resting at the 22.5 centimeter one. And that's the same for all of these. On the Newton balance, it would have been stretched such that it was reading at 2.85 Newtons. That's the same for the NB1 and NB2. They just both had different amounts. And for the weights, I must have hung up a 2 Newton weight and a 3 Newton weight. Or I had a stack of ones, because they are kind of like coins, and I stacked 2 on one and 3 on the other. Okay, so that's just where those information is coming from. And some of them are up and some of them are down, depending whether you're a weights or a balance. Cool. That's the data table. And the first thing it wants you to do is calculate the net moment about the 0 centimeter position. Okay, I'm going to draw a diagram, a little sketch. You don't need to do that for your answer, but I'm going to do it because I think it's going to make it easier to explain. So about the 0 centimeter position, I am looking at a meter stick. I'll try get a better meter stick than that. We are looking at a meter stick, and like I said, meter stick is the star of the show for this question. So I've got one here, and let's just call this is like 0, all the 0 centimeter, and we've got 100 centimeters over here. Let's just say doesn't really matter too much, but I'm looking for the moments about this part here. I'm going to just, it's a very not elegant big blob there just to show you 0 centimeters, okay? And I'm looking for the moments about that position. So that's where I'm talking clockwise and anti-clockwise, okay? So I'm looking for what's pulling me anti-clockwise, what's pulling me down clockwise. Literally think of this meter stick as if it's the hand on a clock. What's pulling up and what's pulling down, okay? It's asking me to calculate moments. So I'm going to move my other questions out of the way for a sec. I'm going to go write my equation. 100% across the board. If you're ever unsure, pull out your equation and you have already got yourself some marks because it's showing that you have an idea what they're asking for. It's showing that you have an idea what's the appropriate way to tackle this question. Even if you get completely stuck after that, write it down, okay? So that's what I'm going to do first. I've just shown you what they're looking for. So moment is equal to force by perpendicular distance. I'm going to check for you guys if that's in the log, and I'll make a note of it on my sample answer if it is. Okay, so I'll tell you what page. Perpendicular distance. Okay. Actually, yeah, no, that's fine. I'll come back to that one and see if I need to tell you what page it's in your logs. I would say most of them are. Most equations are. So the clockwise moments are the ones, these ones coming down. So those are the weights, but also very important not to forget the meter stick. Okay, so we're going to take our clockwise moments, take our anti-clockwise moments, compare them to get the net moments. The net is kind of like the remainder. Okay, so let's start with clockwise. Doesn't matter if you want to start with anti-clockwise, it doesn't matter at all. I just like the look of that one. So clockwise moments, and I'm going to write it out a bit so that it's really clear what I'm doing. Sometimes I'm writing out extra just to show you guys what I'm doing, but really it's no harm for yourself and it's no harm for your examiner to make it really obvious that you're on the right track, okay? Because later, if you make a small slip on your calculation, they can go, okay, well, they were getting there. They were about to get there. They just, missed a decimal point or something like that, okay? So let's look. We're looking at force by perpendicular distance. So we're going to go straight to our data table. And for weight 1, this guy, he had, and force was 2. The way is it a he? Doesn't matter. And the position on the meter stick, so the perpendicular distance from the center or from the 0 point was 32.1. Actually, I'm going to be smart and change straight away into meters. Keep my SI units. Okay, so notice that those are in centimeters on the data table. And you've got 32.1. That's weight 1. You're going to add in your weight 2, this one. And that one had 3 newtons multiplied by and go straight into meters, okay? You might lose a mark if you did that. It wouldn't be the worst thing in the whole world, but why lose it? Just try to remember that it's there. And then you've got your meter stick and you're going, oh God, how do you know about the meter stick? Way back up in the top question, let's check it back up again. It says that your meter stick was 1.2 newtons and its center of gravity, where was it pulling down on, was at 50.6 cm. Okay, so that was given to you in the question at the very, very beginning, and you're kind of only coming back to it now after doing all the work. Okay, so it was 1.2 newtons. Don't need to do anything with that. Take them as they are, and it was 50.6 centimeters. So we're going to say 0.506 meters. This is something you should be banging away into your calculator. You do your brackets. Your people use different acronyms like BIRDMAS, BIMDAS. Do each one first. Do each of these bits first, and then add them all together, or your calculator might be able to do that for you. If you're struggling with your calculator, if you think you're doing what I've written here and you're getting a different answer, let me know. It might be something going weird, but I'm going to take that as something that most people can do at this stage now. That's not to say you can't ask. In fact, you really should ask, but I'm just going to give you the answer and you can see how that looks compared to what you got, okay? So 3.4152, and what are these going to be? So these are Newton meters, okay? And if you're not sure about the unit, look at what you're doing in the mathsy bit. So you're putting how many newtons multiplied by how many meters, and you've got a unit called Newton meters. And even if sometimes these units have another name, you're not technically wrong if you just write what they are multiplied together. Okay, so it's always good shout to get in the hang of doing that. Okay, those are our clockwise moments. Anti-clockwise moments are next, and then we'll compare our two to see what the net moment was. And we are kind of looking for that there won't be a net moment, all right? So that's another bit of a spoiler, but I'm hoping that you were expecting that anyway. So anti-clockwise moments, and in this case, it's only the Newton balances. So if I go and have a quick look at my scribble of my meter stick here, anti-clockwise are going, I'll just call them AC clockwise, anti-clockwise, and clockwise. They're the ones pulling kind of upwards or moving the, if you like, the handle of the clock backwards. That's only the Newton balances in this case. So it's going to be a little bit less calculating for us. So that's Newton balances. And there are two of them. So we'll be multiplying and adding them all together. Balances. Very scribbly writing today. And again, I'm going straight to my data table and figuring out which ones I need to use. I'm going to do Newton balance 1. And that one had 2.8. Sorry, the pen is not great. 2.85 newtons times 0.225 meters. So just in case you're wondering, that's from here. Okay, Newton balance 1. And then we're going to have Newton balance 2 as well. So we're using everything that we've been given on the data table. Always a good sign, we're on the right track. The second one had a Newton weight or a Newton reading of 3.40. Leave that as it is, and it was at the 81.3 centimeter mark on our meter stick, so it's going to be 0.813 meters. Again, I'm just going to give you an answer for that and see if you got on okay. And we have hopefully something pretty similar. So yeah, it's coming up at 3.4054. I have, again, Newton meters. And the question asks us for the net. So net is equal to clockwise minus anti-clockwise. Doesn't really matter which way you go. And in this case, it's looking good. You're not going to have much net. That's perfect. That will be my first one, 3.4152 minus 3.4054. And you're going to be left with a pretty small number, 0.00975 I have Newton meters. It's in the clockwise direction. It didn't actually ask you, so you could probably leave that off. But what I mean is, it seems like there's slightly more moments going in the clockwise direction than there are in the anti-clockwise direction, but it's so tiny. It's not a big deal. I'm just going to say it for kind of completion for my own, for myself, just so I know which way it's going, but they didn't ask me for that. Okay, so clockwise. Correct. That's the moments. You have probably conquered the hardest part of the question now, I would like to think, and it's kind of downhill, I hope, from here. So let's have a look at the next part. It says calculate the net vertical force acting on the meter stick. I'm just going to move the very last part out of my way, so I have lots of scribbling room for calculations, even though these ones aren't too bad. Oh, sugar. And let's try that again. So we're talking about forces now. And in a way that's easier because we're not talking about anything to do with moments, and it's kind of a little bit more like adding and taking. Okay, there's a bit less multiplying. So the net force acting on the meter stick, and we know that we've put forces down and we've put forces up using our balances and our weights, and we are literally just going to tot them up and compare. Okay, so it's a good bit easier. So if you're sticking with me, well done. We're getting to the bottom of it. Okay, so the net vertical force acting on the meter stick, let's say downward. And this is where it's handy to just look at your diagram, okay? So downward forces, I'm going to call it FD, okay, is weights and meter stick again. So these are the forces. These aren't the turning moments. Okay, they're just the forces. So that's much more like I can say my weight 1 was something like, it was exactly 2. My weight 2 was 3 newtons, and my meter stick was 1.2. Meter stick. Getting ahead of myself. And that's quite simply 6.2 newtons. That's just adding on your calculator, and I'd be kind of worried if we weren't able to do that now. Let's do upward. And again, what we're doing is we're going to find the down, we're going to find the up, we're going to compare to get the net vertical force. Okay. So if you maybe not the greatest combination of letters, that's okay. We've got, these are just to make it clear, these are only going to be the Newton balances. So we're going to have our 2 readings from our Newton balance 1 and Newton balance 2 were 2.85 newtons plus 3.40 newtons, giving us 6.25 newtons. So pretty close, a bit of a difference. And our net is going to be the ups minus the downs, or whichever way you want to do it. If you did it the other way and you get a minus answer, that negative is really only telling you which direction it's going in. Okay, so I went up minus down, and I got 6.25 minus 6.2, giving us a 0.05 newtons, which is pretty small newtons upward. Okay, that's it. That's your answer. You aren't doing any more with it just yet. And then you're going to come in with your explaining part, okay? For that, I'm going to use some text that I have from my sample answer. And again, like we've been doing all along, we'll have a look at it, make sure we understand it. Absolutely come back with any questions if it's not feeling super clear, especially for those explaining parts. I said at the beginning when I was going through the questions that when you see and read explain something, oftentimes the best thing to do is to define what that thing is and then compare to your answer. Okay, that's exactly what we're going to do here. So I'm going to paste it in so we can have a look and see how I went about that answer, and give you just an idea of how you could answer your question. Also giving an idea if you have an answer already, are you on the right track? So I've taken this from just a textbook. It's a definition of the equilibrium, the laws of equilibrium. A body is in equilibrium if, number 1, the vector sum of the forces in any direction is 0. So we've just taken our forces up and forces down, and they're pretty close to 0. The net force is 0, close enough for a given experiment. And the second kind of situation that they have to satisfy to be in equilibrium is that the moments about any point is 0. So those clockwise and anti-clockwise, the net clockwise, are there. They should be 0. So that's equilibrium. Now explain how my results in my experiment, or our students' results, verify those laws. So these results verify the laws of equilibrium because the net moments about the 0 centimeter point, it could be any point, are 0.0975 Newton meters, and this squiggly equals, it means approximately equal to 0 Newton meters. There are so the net moments are approximately 0, and the net vertical forces are also approximately 0. Okay, you could just have said that without putting in any kind of numbers. You could just say my net moments are approximately 0 and my net forces are approximately 0, and those are the 2 things that we need to tick the box. We say, yep, I've got my forces are nearly 0 and my moments nearly 0, so I'm in equilibrium. You are done. You can move on and pick what question you're going to tackle next. I'm going to give a little extra piece because somebody, if you're pretty observant, you might go, well, they're not really 0, they're 0.05. That doesn't seem like nothing at all. So I'm going to do a little calculation here. I have for you a calculation to work out percentage error. And it's a really good way to be thinking about results in physics, because we can get caught up with, oh, but I still have a little bit. But is that little bit 0.5 of a force or 0.05 newtons is not much in this experiment that we're doing now at all, we're happy to equate it to 0 or say it's approximately 0. But if you're doing a different experiment with different values, that could be a really big deal. That's why percentage is important. So percentage important is percentage error. How much of an error is it compared to the figures that I'm dealing with? Okay, so in the moments, that one is sounds a bit smaller because it's 0.00975. But comparing that to, and I just picked, is it the clockwise, anti-clockwise one? I picked the anti-clockwise one. So preparing that little bit left over compared to the anti-clockwise one, getting a percentage, so just divide one by the other, multiply by 100, it's actually 0.03% of an error, of a difference. That's quite small. It's not even like 1 or 2% is even small, but 0.3, tiny. We're happy to say that that's approximately 0 in this case. I did a similar thing in the forces. I just said 0.05 compared to my 0.62. And multiply by 100 to get a percentage. You got 0.8 of a percent. So pretty tiny, happy enough to go to 0, especially for something like this where you're working on lab, you've got your meter stick, there could be error in your electronic balance, there could be error in how you read your meter stick, there could be error in your Newton balances, your weights could be, they're probably pretty reliable, but you know, there's lots of different places that you could have come up with a little bit of error and in this kind of experiment. So to be here where you have like less than 1% means we're happy enough to say that, yeah, this is definitely satisfying the laws of equilibrium, okay? There's a few extra bits in there that you may not have needed, but I'm hopeful that they helped you to understand what's going on in this experiment. That's it for that one. Again, I know that is probably quite a long video, but I'm hoping that you picked and chose what bits you needed to look at. If you have tried it out for yourself, if you got stuck or you didn't get stuck and you watched the whole video and there's still things that you are not sure about, I really want to hear about them. I'd love to hear about them. Make sure that if there's something in the physics that you're not getting, if there's something in the way that the video has been running, didn't look too good to you, or you got thrown off or whatever, I definitely want to know about it, because I really am just hoping to make it so that it's easier and you can be more sure that you're well prepared for your physics exam at the end of the Leaving Cert. Okay. The best ways to contact me, I have the Physics Help Instagram, but also, and let me just write it down here, my email for physics is the quickest one because that's what gets checked the most, and it's just info@physicshelp.ie, physicshelp.ie. Okay, and I'll have it linked and things like that in the YouTube video. The sample answer will be available as well, and I will pull out which piece of the marking scheme applies to this one. So if you're feeling really good about it, you want to go back and kind of grade yourself, see how many marks you would have gotten, that's totally valid exercise as well. And again, any questions on that, let me know too. Okay, thanks so much for watching, and I hope it helps.